So let's see, hide floating reading controls. So a couple points. One thing we like to have is the more the students talk, the better. And so maybe let me insert just some points where I can type it so that we can see it. So I think people learn best by doing rather than watching. Let me draw a picture here to give us something to think about and talk about. So there I've drawn a picture. Can somebody tell me a math problem?
4 times 3.
Ah, I like it. And what's your answer?
12.
Sure. So I gained 2 points for Lisa, and I've lost way more than 2, so I'm still in the red. Let me do something a little funny here with this. So I'm getting, seems like I have 17 things that look like this. Or did I count them right? The way that I counted was by putting a dash like that along it. We have 12 things that look, that can't be right.
Yeah, I think it's right. You counted it correctly, Mr. Auckly.
Uh-huh.
Yeah.
Why am I not getting the number Oh, I know why I'm not getting the number that I expected here. I want to do something slightly different with 4 times. I'm changing the picture. What a fail. I wanted to do like this model. Which is also a 4 times 3 equals 12. In this case, we're looking at the dots. But now I want to draw a separate thing. And the separate thing that I want to draw, maybe I'll draw it in colors. So I get 6. Three, 4, 5, 6, 7. Maybe I'll color code this a little bit. 6 things that look like this. I got 7 things that look like that.
Could be 8 also.
Did I get 8? Did I miss
Yes.
it?
That grid's a 4 by 2 grid, David. not a 4 by 3.
I'm counting dots here. So I'm counting.
I
Okay.
get 8 could be a possible answer also.
How did you get 8?
Counting the squares, 1, 2, 3, 4, 5, 6, and then that's by 1 by 1, and then 2 by 2, overlapping.
6, and then this is 6 1 by 1, and then we get
And
2 2 by
2 by
2s.
2s. Yes.
I like it, which is going to be here and here. And then, in fact, I could put one more thing in here just to make it more complicated. I can put 1 by 3s, and I get 2 1 by 3s. And even then, not done. We could add in one more thing, maybe like this. And 1 2 by 3. So let's see. What do we have here? We've got 6 2 2 7 1. So what do we see? I see 6 2 2 and then 7 1. So anyone want to tell me some math with those numbers? Tammy? Are you there? With Zoom, it's kind of hard to tell if people are online. Glenda, are you there? Say hello if you're here. At least get a hi.
Hello.
Okay, so now that I know you're there, ha ha ha, evil math teacher laugh. 6 2 2 7 1. So what might you say here? So what kind of things are you tempted to do if I give you a list of numbers?
I'm tempted to add them.
Sure. So if you add them up, 2 plus 2 is
4,
plus 6 is
10,
plus 7.
17, and 18.
So 18 what? Just because you've got numbers, it doesn't always make sense to add them. I don't want to add dollars and cents. That's kind of a weird thing to add. But in this case, is there something that we could describe what this 18 is?
Shapes, different, or I guess, yeah, I mean, they all look,
They're all shapes. Is there a more specific kind of shape that we're having here?
I want to say rectangles, but I mean, to me, there's two that look like squares. So
Yeah, that's
it's hard for me to, I mean, I think it would be hard for me to say what it could possibly be, but I mean, that's an assumption I think I'm going to make, is that they're rectangles. So
so here you just brought up a great thing in terminology is this puppy a rectangle? And this is one of these things that, sort of a Venn diagram kind of thing often helps. In standard geometry terminology, a square is a rectangle. It's a special type of rectangle, so you often notice what's special about it. And it's like if you have a really tall kid, if you had a 6'7" kid in your classroom, probably everybody would refer to him as the really tall kid, even if his name happened to be Devin, right? He would say Devin, the really tall kid. But you don't have to. You could just say it's Devin. Here, this is a rectangle because a rectangle means it's got 4 right angles. That's it. That's what a rectangle is. And so this means that there's a different type of operation we have here. The operation is, if I put 4 dots this way and 3 dots this way, when I combine them together, I could have 4 star 3 equals 18. And this is the number of rectangles. So part of doing this is I want to take us away from a place where we know it, so that, hey, people that have their multiplication table memorized, glorious, great, good for you. But a big part of the reason we do mathematics with our students is to teach them to think. And the place where it's really important to think is when it's something unfamiliar and you don't know the answer. Those are the things that you can't figure out just by asking your smartphone, hey Google or hey Siri, what is? And so I want people to spend some time thinking about this star operation and try to figure out, compute more examples. Examples. Work several out. I know that 1 times 5 equals 5. 1 times 53 equals 53. Is there something star 5 that equals 5? Is there a 1 for the star? I know that 14 times 13 equals 13 times 14. Is 14 star 13 equal to 13 star 14? For that matter, what is 13 star 14? Do you need to draw and count? Are there other properties? Is there a star table? Right, there's certainly the multiplication table, right? I could do 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 2, 4, 6, 3, 6, 9, right? We've all done this before. In fact, when you're doing the multiplication table, you're really just doing bunches of examples of multiplication. So now I'm going to stick you in breakout rooms, maybe size roughly 5 each. And I want you to write on paper, share thoughts. I'm going to have you report back on these. Let's see if I can figure out the Zoom controls well enough to do breakout rooms. Go. So how many participants are we right now? $22. If I do recreate. Okay, so I have to be quiet. I'm doing a thing. John, yeah. Is somebody gonna wait? Mateo, are you there? I see you haven't joined the room. 11:15. Hi, Stephanie.
Hi, actually, let me just see, what am I doing here? Let me look at my view options. Okay, got it.
Yeah, I've turned off my video. I'll turn it back on. I'm hoping, were the people in the, did you join one of the rooms?
Yeah, but I'm not participating on it. I'm just, this is beyond my math capabilities, far beyond.
Ah, well, this is one of the things I hope to impart to people is you can play with it. Getting 1,000 wrong answers and one insight is a really wonderful thing. Thomas Edison would ask, how does he invent? It's like, well, 1,000 bad ideas and one good idea. Nobody remembers the 1,000 bad ideas. Just start saying stuff and thinking, and you'd be surprised what you can do. That's part of our philosophy is we want to give people
Yeah, no, that's really wonderful. And it's so different from the way most of us were brought up with math, where it really was extremely rigid. There was a right and a wrong. Somebody knew who the right was and what the right was, and you either got it or you didn't. So
yeah. Math does have right and wrong. You can figure things out, but you can own it, right? In the question, there's no right and wrong question.
right. Mm-hmm.
Bringing people back here in a second or so. The rooms are closing. In 30 seconds, we'll be back and I'll take notes so people can annotate, or we can do a little bit of both. Okay, I think we are back. So, did folks have progress thinking about this? What did people discover? And actually, while you're getting ready to talk, let me make a couple of points here. I think it's incredibly useful for teachers to suddenly be thrown in the role of students to remember what it's like. It's very easy to ask a question and then immediately answer it because it seems like you're waiting for it forever to answer. When you're in the role of student, it takes you a while to get your words out. And so experiencing that. In my house, I have two kids, my beautiful daughter, Lyndon, and my crazy son, John. And seeing them go through school has helped give me a little empathy. They both got a little behind in homework. My son really got behind in homework. And the end of the semester was just crazy stressful, whereas I was trying to support him and help him and encourage him to get it all done. I think I'm a wreck just from watching him. It's good to see and know and understand what things help your students. And so also other points are, if you've got a problem like this, where people haven't studied it, this is a great sort of thing to explore if you've got students that feel that they're behind or won't necessarily feel, because it can give them confidence, because it brings everybody back to the same starting point. Nobody's studied star products before, this sort of thing. So now with my preaching done, I've at least got you to think for 10 minutes, hopefully talk for 10 minutes. What can you tell me? Joy, what did your group do?
We actually tried to figure out an operation or a pattern on the original figure that we have for the 4 times 3 equals 18. 4 asterisk 3 equals 18 rectangles. So we kind of look at the numbers written down on the pattern that you wrote, 62271, and we kind of stopped at looking at how we can generate the 18 rectangles. We did not really actually, but there was, I'm not sure who was that, who shared the interactive board with our group.
I should have asked folks to take a screenshot of it so we'd have to share.
I know.
We'll do that the next
That was,
time.
I think that was Priscilla.
Yeah,
the
my
66
internet, the wind I think is making my internet go off and on. I did share, I was typing it and it got erased again. On what I was saying, can you hear me?
Yes,
Oh man, hello.
I can hear you.
Okay, so what I was saying in my group was, I don't know why I'm thinking this, but we do know that 13 times 4, you know, I punch it in, it was a 182. 18 is very important to this problem, and 2 is very important. So I was looking at 2 times 2 times 2 times 2 makes 16, and then add 2 more would make 18. So the 2 and the 18 are very important for some reason. That just came to my mind. So I was thinking possible probability is what I was doing. I don't know how to explain that, but my mind was just racing in that direction. That's what I shared with my group.
Sure. Rochelle, what did your group say?
So our group probably didn't understand the problem. So we had one of our group people share the screen and redraw what we thought might have been, but we just ran out of time.
So do you understand the question now?
Still a little vague for me anyway. The others may understand.
So yeah, if we don't understand the question, we're not going to get there. So we'll try it. Let's see if maybe the others. In fact, this is a wonderful test. Is almost always students are really bashful about speaking up, and partly it's just psychology. You feel that, oh, everybody else has to know the answer. I do things like, the low cost clicker is I will have people stick their head down on the table and raise their hand in order to answer a question so that nobody else knows what they're answering. And I'll say, okay, how many people are confused about this? And all the hands go up. It's like, Okay, look, raise your heads up now, and I'll tell you, everybody was confused, or only one person out of a 30-person class got it. I guess I can pick on people and be mean as part of what a math teacher is. Joseph, did you understand the question? Are you there, Joseph?
Yes, David. Sorry, I was on mute. Yeah, honestly, I wasn't able to make a screenshot for the question, and I was with Rachel's group, with Larry and Ellie. So, one of my group mates, like Larry, tried to show us the model on the Word document, like modeling the 3x2 dots. We also talk about the operations, like instead of using the asterisk, we also use the dot as we're thinking about the operation. So
Awesome. I like this 3x2 dots. I'm going to try. So did he draw it like that, or did he draw it vertically?
Yeah, Larry showed us like the 3x2 dot, like that. 3x2.
So one of the things I make my students sometimes yell. In fact, I'm going to have everybody unmute. Unmute now. Come on. Let's do it.
Okay.
We can do it. Everybody unmute.
Yep.
Unmute. Please unmute. I want to get a great big Zoom yell. For a Zoom yell, I want everybody to yell.
Yow.
Rock. 1, 2, 3. Yes, this is exactly what it feels like to be a student. Really? You're expecting me to do this? It's what hour? It's on a Saturday? Yeah. It's important to interact and do things, grab a teddy bear, throw it around the classroom, have some levity. We're trying to, in this thing, we're counting squares and rectangles so we can draw pictures. Right? I see a square here. I see a square here. I see a rectangle. In fact, if I color code these the same way, I was using green for my 2x1 rectangle. I get that. Do you see how these rectangles correspond to this grid of dots? I'm pretty sure this shows us. What does this tell us? 3 star 2 is equal to?
3.
3.
Awesome. So in fact, one of the things we can do is start to fill in. So let's try to say the rules. Let's get somebody else to say the rules. Marty, can you describe? You can tell me things to draw. If you want me to do an example, describe the example. I'm going to mute everybody but Marty if I can get my control. Because now that
I can't hear you. Somebody's mumbling. Sorry.
Yeah.
Okay, yeah, I can hear you now.
I just muted everybody. Marty, if you unmute, you there?
Yeah.
Okay, so can you describe the rules of this?
For the 3 asterisk 2 equals 3, is that what you're asking?
And more general, how we make the asterisk of 2 numbers.
Okay, so that there's 3 rectangles and 2 types of rectangles is equal to 3 types of rectangles.
Is that enough of a description that if the only thing you saw was 3 types of rectangles, would you be able to reproduce this with the bigger thing of dots? Rochelle, does this explain to you what's happening? Or let's try to be more precise with the language now, just to describe what happened. And so, in fact, if you're going to explain what happened, I might put a phrase here that might help you. So, Marty, I'm going to pick on you a little bit more. Hold on like a rabid dog. Can you use this phrase, examples rock, to help explain this?
Okay, so well, we started off with the 3 by 2, the 3 dots by 2 dots, and then we drew the 2 squares, 2 smaller squares, and which are 1 by 1, and then one other rectangle, which is a 1 by 2.
Sure. So could you give us another example to consider?
With the same number of dots?
I think we could use different numbers of dots. There's nothing that says we have to use the same numbers of dots. I want an example that will illustrate and help people understand the problem.
Okay, if we did the 4 by 2, we would have the 3 1 by 1 squares, and then we would have a 1 by 4 rectangle, 1 by 4.
So we have 3 1 by 1s. You would have 1 by 4, which will be a bigger one. I don't think we've. Wait, 1 by 4?
Wait, 1 by 3. Sorry.
How many 1 by 2s do we get?
Where are we at? Okay, so we have 3 1 by 1, and then 1 if we have 1 by 3.
Oh, we have 1 by
or 1 by 2. Yeah, we can have 2 of those, right? 2 1 by 2s. And then 1 1 by 3.
Sure. And so what is the grand total?
So we have 6.
So can you enunciate what's happening? So as soon as I give you the numbers if I gave you the numbers, let's do crazy size numbers for a second. If I gave you the numbers 7 star 11, what's the first thing you would do?
Okay, I would it will be the first one would be the 1 big rectangle.
And where do I see a rectangle? So you can do this in your head, but is there something that might help?
There'll be a 6 by 10.
So we're seeing the 6 by 10. And how did I still, without something else, I can see where you're getting the 6 by 10 in the back of my mind, though I can't see anything here. Is there something? So Priscilla's adding, I would add 7 plus 11 to come up with 18. 3 star 2, I would get 5 rectangles we're seeing from Priscilla. So I'm getting some comments here that we need to address. So let's come. So Priscilla, how did you get 5 rectangles? We drew out the rectangles. We saw a blue square, a green rectangle. And so that gave us 3. Are we missing something? What did we miss? And if you're saying it's 5 and we've drawn a picture that's 3,
I think I recounted one square, sorry.
and so do you agree with the 3 now, or are we wrong?
My mind is racing, hold on.
Sure.
Okay, I see what I did. There's 1 by 1, there's 1.
Wait, there's 1?
Oh, no, 1 by 1. I have 3 squares.
Wait,
1
I'm
by
looking
4.
at, you see the screen? In here, if you look at 1 by 1s, how many 1 by 1s do you get?
Or I'm doing the 4 times 2. I'm sorry.
You're doing the 4 by 2. Okay, so let's do the 4 by
Sorry.
2. So if we do the 4 by 2,
Okay. Marty and I, we usually do this. That's the reason why I'm kind of like, I take off what she's thinking and then I throw something back to her and then she throws it back to me. I think I got lost in the vibes of talking to each other. So I think this is what I was thinking. For the 3 by 2, what are the possible ways? How many possible ways can I get the rectangle? And the way Marty said, I see 1 by 1, so there's 2 of them.
Okay.
And then she sees a 1 by 2. She sees 1 of them. So let me show you. Maybe I can show my video, my camera.
Yeah,
Hold
you want, I'll stop my screen share and you can show if you want, or if you want, you could just annotate on, if that's easier. Either way, press start share or annotate.
Now, I don't know why I was thinking that, but when Marty was talking, that's what I was drawing when she was doing the rectangles. And somehow, okay, 1 times 1 is 1. 1 times 2 is 2. So I took the product. 1 plus 2 is 3.
I see. So there you're trying something like you're making it. This is what I would call a conjecture. Woohoo! We love conjectures.
So the same way with the 4 by 2. The 1 times 1 equals 1. The 1 times 4 equals 4.
1 times 1 equals 1. 1 times 4 equals 4.
4. 1 times 2 equals 2. And then I added up the results, the products. I think that's what I did. But anyway, that kind of makes sense with the 18. I was trying to figure out how to make 18. And I think by adding up the product of how many squares there are possible, I went and added the answers. That's how I came up with 18. I don't know if I'm on the right track, but it's just.
You're at the stage of exploration. Let's explore and see where things go. And as we explore, before we explore, an important thing is to make sure that we can enunciate the question so that we can all be thinking about the same question. There are many, many questions we could ask here, but let's talk about what the possible questions are, like Ray discussed, and then let's settle on a question. Here, I didn't give you a choice of what to choose the question. I kind of chose the question at the beginning, but now we're exploring it. But I want to understand how to explain the question. Can somebody, when we were doing this example where we wanted to explain the question with 7 times 11, maybe try to think about a recipe? How would you understand this? Not how to solve it, but what's the first point that might really help you understand this that we should do here? I have something in mind that. So if you're doing the 7 by 11, what's the first thing you're tempted to do? Anyone?
Okay. Okay, so. So for the, I'm wondering on the first one, we had the 4 asterisk 3 equals 18. So when I do 3 times 4 plus 2 times 3, that gives me 12 plus 6 equals 18.
Does that have anything to do with it, or is that a coincidence? That's a good question. Oops, I'm not scanning this very well. Let's scroll. So 4 times 3 equals 12. 2 times 3 equals 6. 12 plus 6 equals 18.
Mr. Oakley, just a quick question.
Yes.
When you make the rectangles and the squares, are you always allowed to have the squares or rectangles around the dots? And when you make those squares and rectangles, can they overlap? I just think that there has to be a clearer direction on how to do this.
Yes, that's what I'm trying to get, is I'm trying to get one of you to enunciate the question. I have some rules in the back of my mind, but here you're asking some beautiful questions. Can rectangles go around dots?
And can they overlap?
Overlap. So I think one of the things that should be almost automatic, we're talking about rectangles somewhere. So what should we have when we're having a discussion of 7 star 11? If I give you a math problem and it starts with a certain triangle is made by a light pole, a person, and their shadow, what would you want your students to do as soon as I make that phrase?
So with the 6 times 10, you could do 6 times 10 and then add the 7 by 11.
So one of the things is just making up things to try is a great way to compare and see if answers line up. But you ultimately, when you're figuring out what works, you first make guesses and see what's going to work, and then you look for patterns. And if you find some pattern that appears to work, you then have to ask why. Just because a pattern happens to work, it might work in one case, but it might not work in another case. Maybe we'll get to a place where we can do an example with that in a little bit. But before doing this, the first thing we need to do is enunciate and understand the problem. And I'm worried that that we haven't done this part here. And there's one task. If I say a triangle, dot, 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 what should happen at this stage? Or what should happen if you go a little bit further? What should appear on the piece of paper? Alan?
The triangle has 3 sides.
Yes, but what would you want your students to do if the problem had the word triangle in it? Right? There's
That you do the measurement of the square and then divide it by 2.
that's when you're finding the area of a triangle. What I was hoping to get at is the phrase draw a picture. So the role of this, and one of the things that I want to do as an instructor, is I want the students to figure out the answers. What I want to do is tell students problem-solving techniques, things that work in many contexts. If you're doing a geometry problem, if you see a word triangle, square, rectangle, if you see a shape in a problem, that's a big clue that you should draw a picture. Picture's worth 1,000 words. This is a great problem-solving technique. So let's go back. If we're trying to understand 7 star 11, what's the first thing we should do?
Draw your
Draw a
picture.
Yeah,
Draw
and
the
what
dot.
should it be a picture of?
The dot.
The dots, yes. And so the dots are going to have, and how many dots do I have in which directions?
7 horizontal, 11 vertical,
Sure.
or does it matter?
Ah, good question. 1, 2, 3, 4, 5, 6, 7. Oh, yes, it does sit. Okay, so obviously this one is rather large, but it is going to show something to us. So first, draw a grid with 7 dots horizontal and 11 dots vertical. And we just had a question of, is the answer at the end of the day going to matter if I'm looking at this thing like this, or if I'm getting sleepy and I turn my head to the side? And so if I put them horizontal or vertical, does the orientation matter?
No.
Are you sure about that? Why?
I don't think it matters. You could just turn your paper. I don't.
No, right. You can just turn the paper. Awesome. We did this incredibly quickly, but in a short bit, this is one of the things we really want to do. We want students to ask questions, even if they can't answer, just asking the questions. So who said this? Who I didn't catch. Who asked who does the orientation matter? Who said that? Who said that?
Sue asked if the orientation mattered.
Yes.
Is that what you're asking? Oh,
Yeah.
I don't think I asked that.
Or who had the question about, does it matter whether the dots were horizontal or vertical? Somebody got us off on that line. We were telling us to draw the picture. Is that Anna?
I don't think so.
If I was a heads-up teacher, what I'd like to do is I'd like to put a name here. One of the things that I do in my own classrooms is when students ask questions, I will write the question and the person's name up on the board, and I'll leave it there. And I can even put it up again another day. I'll use poster paper and write it, and I'll start hanging the posters up around the room where people can see their names and their questions, and then we leave it open until it's figured out. One of the steps that happens when there's questions is you first often get to a stage where you'd have a guess or some intuition about it. You might not know exactly why, but you might somebody, and sometimes it's hard to come up with a guess. Like here, I don't think we have an accurate guess of how to do this star operation yet. But if somebody gives this, we can name it so that they can own it. And then we look for an answer. And we put the answer, right? And so it's the question, the answer, and the reason. The reason is super important in mathematics. We don't want to stop just with an answer. We want to understand the reason why it works. And so coming back here, we wanted to draw. So when we talk about some questions, can rectangles go around the box? Do we mean like this? Does this count as a rectangle? When they surround, does something like this count as a rectangle? So as you understand the question, do these two green things count for us?
No.
No. And so in fact, how does the rectangle have to be oriented? Does a rectangle like this count for us? Bad rectangles.
Well, it could.
But as we phrased the problem, when we did the problem up here at the beginning, did we allow tilted rectangles to count?
No.
No. And so we're not allowing, so over here, we're calling this bad because it's tilted. Why are these rectangles bad, right? Here we've said the answer. I've said that it's bad, but I didn't say why.
Actually, I think those would be okay. Because if you say that those are okay, you can have one involved in your array. Otherwise, it starts with two, doesn't it?
Great question. Does it start?
You know?
There's different questions about what you. So let me, David, just to make things. Do I count this? So is this one rectangle, two rectangles, three rectangles, four rectangles, etc.? Is this okay?
Where are you?
I was here on the screen and I was drawing a bunch of rectangles and squares that just went around that dot.
No, that's just one. No,
because I could get infinitely many different rectangles surrounding.
Sure.
I need to put some constraint on the rectangle in order to have a problem. You came up with a really interesting question. If we don't allow, then you would need to start at 2, right?
Right.
2 unless. And so that's kind of telling us that 1 star 5, 1 star 17 are things that we might
Would be-
know the answer to. You kind of have a picture.
Right.
of it. And so this is David.
Yeah, there it is. Yeah. Okay, let's see. Got it.
Right?
Right.
So, which I absolutely love. This is helping us. I hope this is helping us understand the problem. So in fact,
Like
not only-
1 star 5 would be 5, right? 1 star 17 would be 17.
Oh, let's see. 5, 17. Let's think. I'll put those in. So here I'm going to put David conjecture.
I'm thinking,
5, 17. Before we can answer this, we need to understand the rules. And here's something
Right.
that's important when you're understanding things. You want to understand both what works and what doesn't work, because what doesn't work helps you understand. And so we said that these are bad rectangles because there's way too many. What do you need to have so that you don't have infinitely many rectangles? So how are we constraining the rectangles? Where did the rectangles go in the picture? I slightly drew it a little differently here. Maybe I'll draw it like this to try to be more specific for my blue rectangle. I drew them small because I didn't want to mess up the picture. See what I'm doing there with that 1 by 1 square? Or here I'll draw a 2 by 1.
right.
So what am I doing with those rectangles?
You going through going through the dots?
And what part is on the dots? Be more specific still.
Those 2 rectangles that you've drawn, you've actually used the dots as corners.
Awesome. That's got to be one of our rules. So first is
Okay.
draw a grid with 7 dots and 11 dots. You notice the example makes this easier to understand. If I wrote A and B or X and Y, the notation would be more general, but humans don't understand this algebra stuff. And since we're humans, it's going to turn out much better for us if we look with a concrete example. Oh, you know what? Let me undo that. I'm going to leave that, and instead I'm going to copy this and paste it so that we can continue to talk. And then we'll get the rules specified. The dots are a little dangerous on my Zoom. They tend to knock things out if I'm not careful. So I'll save here in a second. And so, there we had rules. First, draw a grid with 7 dots wide and 11 dots high. Does that make sense? And so it's specifying the problem.
Yeah.
Second,
Yeah.
draw rectangles with, and there's a first point, and that should be corners on the grid.
Must be, yeah, vertices.
Yeah, rectangle corners on grid. Does that make sense the way I've said it?
Yeah.
if anybody has a question and doesn't understand what this 2A point is, yell. Also, there's another condition that we said up here. Do the rectangles, so what about the sides? Can the sides be at angles?
No,
So what do the sides have to be? What do we need about the sides? Seems like there's another condition. Corners on the grid
vertical and horizontal sides.
and vertical and horizontal sides.
Right.
Awesome. Let me ask another question. Is this an allowable rectangle? Did we do something like that yellow line when we were doing the 4*3?
Has to be at least 1 by 1 or 2 by, I don't know. We did not.
We did not do ones like that. So there's some rule here. What do you think the rule is that I did not enunciate about the rectangles?
Has to have 4 corners.
Okay, well, it must, so in this rectangle, we're going to say must have 4 distinct corners would be, as a mathematician, because things don't have to be distinct would be one way to do it. Sure. Or must have
Right.
area, or must have side length
Vertices.
bigger than or equal to 1, right? That's a C1. Equivalently to must have positive area. Equivalently, each side.
Must have.
This was a greater than, let me just say, let me write that positive.
Right.
Each side must be positive. So, in fact, I'm claiming that these 3 conditions are all the same. I'm not telling you why they're all the same, but sure, these are the conditions that specify these rectangles. And then the problem is to count how many rectangles. So the third thing is meeting 2A, B, and C. Does this now define the problem so that people understand what the problem is if they see this on my screen? If I was doing this, I'd be tempted to type this up in rules later on and to the students that let them look and play with. Yeah, so that it's easier for them to see, at least write it up with neat handwriting, not a mouse on the computer screen. So far, so good? In fact, now that you have this, you could start thinking about looking for general patterns to see things. Like somehow somebody was saying something really rather awesome up here. Let's go back to things. Somebody said, look at 6 times 10. Where did we get this 6 and 10 out of this 7 by 11 grid of dots here?
I
So
think the 6 times 10 is for the 1 by 1 square.
Yeah, and so when we count the 6, if we have 7 dots, we have 6 gaps. Which in fact, you see what the rule is? If we have 11 dots, how many gaps do we have?
10.
You have 10. And so what are you doing? If I tell you we have 43 dots, how many gaps? Can you tell me there?
42.
And what did you do with 43 to get to 42?
Subtract 1.
Subtract 1.
Uh-huh. So this is 43 minus 1. This at this stage is still at the conjecture stage. It's at the conjecture till you can say why. And so the reason that I would say that there are 6 gaps when there are 7 dots is I will count the left end of each gap. Each gap has a left end and a right end. And if you see, I've got this first dot is the left end, the second dot is the left end. Every dot seems to be the left end, except this funny dot here on the far right can't be the left end of the gap because the gap can't go off. You understand why the last dot can't be the left end of a gap? Does that make sense? Because I'm drawing the gaps. I start at this dot, I draw a gap. I start at the second dot, I draw a gap. I do this for each of the dots, but the last dot, I'm not drawing a gap here because there's no other dot for it to connect with. That's why we subtract 1. And so why does this 7 gaps here and 10 gaps here tell us anything about this problem?
So there's 60 1 by 1.
Awesome, yeah. Because when I get the gaps, if I take, say, that gap and I take that gap, these 2 gaps give us this 1 by 1 square. We're starting to make progress because a gap tells us the start and stop here. It tells us the start and stop over on this side. It tells us the sides of the squares when I'm counting the gaps. So for the 7 by 11, we're going to get 6 gaps horizontal and 10. This 6 is a 7 minus 1, and this is an 11 minus 1 vertical gaps. Therefore, 60 1 by 1 squares. Does that make sense? That is definite progress, right? We've just discovered something. When we're doing the 7 star 11, we have to compute the number of 1 by 1 squares. We're now going to also have to think about the number of 1 by 2 squares and the number of 2 by 1 squares. I'm beginning to think we're not going to finish this. In fact, I'm rather sure. But this is a great starting point. Let's come back to David's thought and let's work out 1 star 5 and 1 star 17. Let's work out 1 star 5. So we've actually got a recipe here. The first thing to do is draw a grid. When we draw a grid, for the 1 star 7 or 1 star 5, I'm going to put 1, 2, 3, 4, 5. So, are there any rectangles that fit all 3 conditions in line 2?
No.
Right, because the
Zero.
widest it could be would be 0.
No.
and not allowing people to
Zero.
know width. So we conclude that 1 star 5 equals 0. Without drawing the picture, can you see what 1 star 17 would be?
0.
0.
0.
1 times 1 asterisk n is equal to 0.
This is an answer. Who said that? Can I give a name here?
I actually put that in the chat
Ah,
because I put that considering that's 1 asterisk 1 is equal to 0, 1 asterisk 2 is equal to 0. That means 1 asterisk n is equal to 0.
Where n is any integer.
and this is joy,
Yes.
pure joy. I love it. I maybe shouldn't take liberties with your name, but this is Joy's answer. And you even told the reason here, just to follow up, is going to be, what's the reason? Can somebody tell me the reason?
Because there's no way you can draw a rectangle. Because in our limitation, there should be 4 corners, distinct corners. And if there is only one, one column, or maybe I don't know how to describe that, then we cannot draw any rectangle out of that.
Sure. It's great practice to try to enunciate this. It's also, I think, a beautiful thing. Maybe you're not finding it such a beautiful thing for it to be put on the spot like this, but hopefully it will help you empathize when your students are trying to form words and enunciate the thoughts about this. But this is actually rather tricky and it takes practice. I love the links that you're putting on here about ways to promote discussion. I'll put on the website afterwards. Thank you for sharing. So in fact, one of the things in collecting data, which you can do in a pure math question, it doesn't have to be statistics about how much hay do you feed your horse each day. In fact, collect data is one of those problem-solving techniques that pairs together very nicely with examples rock. And so organize your work. You would have no idea that I know that this is a good idea based on the work you see me do. I do realize that's one of the things I struggle with the most. If you look at my office, it's, oh my God, an unholy mess. But a way to organize might be making a table, because we have a model for this from the multiplication table. I put 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We, by our observations here, figured out that if any number is a 1, you get 0, 0, 0, 0, 0, 0. You get 0, 0, 0, 0, 0. So far, so good? So what's the next example we ought to consider, do you suppose?
2 by 2 will be 1.
Awesome. Oops, 2 by 2. Bing, 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 bing. That's a 1. And we did 2 by 3 earlier. We came up with 3, right?
2 by 3 is 3.
2 by 3.
And both 2 by 3 and 3 by 2, it's symmetric across here.
And 4 by 2 will be 6.
4 by 2 was 4 by 2, 6.
6.
I think we did do it. Yeah, it is.
4 by 3 is 18.
Yes.
4 by 3. That's the one that seems a little bit odd. Most odd there so far. But which direction should we go in expanding this thing out, do you suppose?
5 by 2 will be 10.
5 by 2 is 10. Is it? Yes, it is.
Yes.
6 by 2 will be 15.
Yes.
Oh, how are you getting this so fast? I'm certainly not drawing the dots.
There's already a pattern.
What's
1,
the
3,
pattern?
6, 10, 15.
And what's that pattern? And describe that. Give a rule.
That would,
You're adding one more each time.
So I'm not just adding from 10 to get to 11, 11 to get to 12. What do you mean I'm adding one more?
So adding from 0 to 1 is 1, 1 to 3 is 2, 3 to 6 is 3, 4, 5.
So it seems like we've got a recursive, coming back to the Fibonacci, it seems like you have a pattern that's going to show you how to get the next number here, right? When we go from 15, the next one, we're going to add 6. We're adding the
6.
number above it. If we add these two numbers together,
21.
To get,
21.
21.
so so this is going to be 21. I'm going to put in, to get 2 star in plus 1, looks like it's 2 star in. So here, if I'm thinking n equals 5.
Oh, n plus 1.
And if I want to get to, from the answer with 5 to the answer with 6, seems like I add on the number n. Does this make sense, what I'm writing with this conjecture? I'm using some mathematical notation here. It's a little weird, but. So using this conjecture would be saying that this is if we want to get 2 star 8, that's 2 star 7, which is the 21, plus, and then 7, right? Which is equal to 28. And this is a sequence of numbers you may have seen before. Let me draw these numbers in a different way. Here is the first one, just a 1. Here is the next one, which is a 3. Here is the next one, which is a 6.
Right.
Here is the next one. This is 1, 3, 6, 10. These things are called triangular numbers.
Right. Right.
Okay. So we're discovering things here. Let me point out, so I'm going to give a different question that I'll let you think about and hopefully try to notice something. We haven't answered this question. In fact, I'm going to describe 2 other questions. One thing that I want to point out is it'd be really disappointing to look at this and go, oh, well, but I'd like to do it with my students, but I don't understand it yet enough. How do I understand it? The first thing is certainly you should play with it yourself before you bring it to students so that you have a sense of what it's like to be a student and have a sense of the pitfalls that are going to happen. On our web page here, I have posted something called Intersection Math. This is a write-up of this activity that looks like this. It's by James Tanton, who has beautiful activities for middle school and high school students written up in lovely ways. He has a description like this. 4 times 3 equals 18. I'm going to describe this picture to you. He also has a description with grids, where he's going to get the same sort of thing about counting rectangles, and he's going to come up with
Wow.
This is what we've been studying, is this multiplication number 2. Then he has a multiplication number 3, which I'm going to describe multiplication 2 and 3. And then he has this list of questions that you can ask students to think about and let them explore. And it'd take time. It'd probably take several 2 to 3 30, 40-minute sessions to get students to start making connections with it, which you could do over the course of a semester, right? Is let them play with the problem, collect ideas, send them home. What you'd love to have happen is have students get so engaged that they take it home and they play with it, and they come back excitedly the next day and say, hey, look, Mr. I discovered this and this. Wow, woohoo, and throw a party, get out a party hat and stick it on their head, or, they get out the cupcakes. You love to see this happen. So this is posted on the website, so you can actually read about it. So I'm not going to leave you hanging about this. But if we had more time, I would have you fill in a bit more of this table. It's perfectly reasonable to fill in the up to 6 by 6, just drawing pictures and carefully counting. And that gives you good insight. It lets you know that good problem-solving techniques are collecting data, using examples, and organizing your answers. Let's take then, I'll say, multiplication 2. Put a row of 4 dots. Actually, I'm going to make these much further apart. That's second, put a row of 3 dots beneath. Right? Draw a picture. Third, connect the dots on top with the dots on the bottom. In all ways. So there I see 3. Actually, let me redraw that one. When I do this, I want no triple intersection. So you notice I kind of bent this around so I wouldn't have 3 lines going through the same place. Here I'm getting 3 lines, 3 lines, 3 lines. That's 3 times 3, and then I'm getting 3 more. So if I count the number of lines, that's just a different picture of 3 times 4. It's maybe not your standard picture of 3 times 4. So number of lines equals 4 times 3, I'll do, right? But now I can get a new product. My new product, I'm going to count the intersections of the dots. So count with me. So did I connect all the lines on top with all the lines on the bottom? I think I did. So now I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Am I missing one?
Between the second and third dots on top.
Oh, 18. So here, fourth, count the dots. Let's call this 4 circle times 3 equals 18. Huh. This doesn't look like the rectangles at all, but it seems like I got the same number with a very different problem. Yes? Do you think this is a coincidence, or do you think that that happens to be the same for some reason? What's your guess? Seeing math is beautiful is a wonderful thing. Often people hate math, and if you get your students to say math is beautiful, this is the first thing, is get them to enjoy it and want to play with it. If somebody wants to do something, you'll have a much better chance. I'm starting to run out of our time here. So let me comment that the things that you should do here are, of course, you should work out what 1 star 5 is. 1 star, or this, not star, but circle times 17. What is 2 circle times 3, right? And so if we were doing this, if I had just 1 dot and then I had 5 dots, how many intersections do we get?
None.
0.
Is this corresponding to what you saw?
No.
Right? Do you see what would happen if you had 17?
Mm-hmm.
Right? Humans are good at generalizing from small examples. Let's do 2 and 3. If we do 2 and 3,
Three.
what was 2 star 3?
It's 3.
It's 3.
Curious? In fact, the way I would phrase the multiplication 3, and so my son and his friends are kind of fun to gossip about and watch. Sort of, they all went out in the fall in one combination, then they all sort of shuffled and started going out in another. They had the prom and they went out in one combination. It seems like whoever's dating whoever on 1 week, 2 weeks later, they're dating somebody else. He's a junior in high school. So what we could imagine is that you've got girl 1, girl 2, girl 3, girl 4, boy 1, boy 2, boy 3. This is multiplication 3. How many ways can you have a double date? In other words, 2 boys and 2 girls. I'll put quote double date, but you know, I'm not going to pair off. So maybe let's do this with the 2 and 3. So if I have 2 girls, girl 1, girl 2, boy 1, boy 2, boy 3, then the possibilities would be, so if I do 2 date 3, The date multiplication could be girl 1, girl 2. You've got to have those, and boy 1. You could have girl 1, girl 2, and boy 2. You could have girl 1, girl 2, and boy 3. So it's 3 ways. So 2 date 3 is 3. In our table, we have a 3 here. Is this a coincidence? Yes or no?